Okay, hello guys. So next part of your physics. Okay, so Kepler's law. Alright, so when you reach this particular section, okay, some of the students will start to think, oh my god, what am I learning here? Alright, or you tend to get confused of what you're learning here. But okay, hello everyone. So let's look at your second part of your chapter 3, your physics, which is on your Kepler's law. Alright, so a lot of students when they reach this particular section, you might feel a little bit confused, or you might not know, or you might not actually or fully understand what you're actually learning here. But I would like to say that Kepler's law is actually not as complicated as it seems. Alright, so I'm going to try my best to explain it as simple as possible so that you know what is going on. Okay, once you understand what is going on, you will realize that it is actually not as complicated as it would be. Okay, first law is what you have been learning since your primary school. You have been learning Kepler's law, first law, just that you don't know that is the first law. Alright, because in primary school you learn that your planets are orbiting not in a circular shape but in an oval shape, right? Okay, so that oval shape is what we call elliptical orbit. Basically, that is the first law. Alright, it's what you have been learning since your primary school, even until last year, your Form 3 PD3. Okay, the heliocentric model proposed by Kepler himself. Alright, so basically, this is the model that has been finalized, that planets are orbiting in an elliptical shape instead of a circle. Okay, now, few things that I would like to highlight here about the first law is that um, of course, orbits of the planets in the solar system, alright, is based on the sun. So the sun will be your focal point or the focus. Okay, so everything is calculated based on the orbit of the planet around the sun. Okay, and the reason why you are going in an orbit, what they call elliptical shape and not a complete circle is because you have two axes here. All right, if you see here, you have what we call a major axis and a minor axis. And reason being is that why you go in an oval shape or elliptical orbit is because your major axis is longer than your minor axis. So what do we mean by that? Let me just show you an example. Okay, so if I were to draw you a cross, so assume that I'm drawing it like same length lah. Okay, so if you were to complete the diagram, you will notice that the circle here is more round, right? But if I were to lengthen this one, what happens is that this will become an oval shape, which is what the planet is doing right now, orbital or elliptical orbit. And the reason being is because the axis here, the major axis here is longer than your minor axis. Alright, so in which condition will the planet orbit in a circular motion or circular orbit is when the major and the minor axis are at the same length. Alright, so that is why I highlighted here. What happens if the major axis is the same as minor axis? So instead of elliptical, your planet will go in a circular motion. Okay, so that is it. Okay, that is it. That's it for your Kepler's first law. Alright. Okay, or normally what they call as the law of orbits. Is basically just mentioning how the planet orbits around the sun. Okay, so no formulas here. It's all just explanation. Alright, so I've just pointed out all the important characteristics that you need to know. Okay, second law, which is the law of area. Now, this is the part where a lot of people will get confused. Okay, they might not really understand what is going on right here. Alright, so of course I do not wish to dwell into this definition here. Alright, a line that connects a planet to the sun sweeps out equal areas in equal time. Oh my god, even I don't understand what he's trying to say. Okay, but alright, before I show you this, let me show you a simple analogy. Okay, this is me and my stickman. Alright, this is situation number one. So let's say if I'm traveling from point A to point B, for example. Alright. Okay, so the total amount of time travel is, let's say, 10 seconds. Okay, this is situation 1. Now situation 2, still me, always will be me. Alright, okay, same amount of time, 10 seconds. Okay, so let's say that AB, for in situation 1, in 10 seconds, I was able to travel, let's say 10 meters, meaning from A to B lah. Okay, 10 meters. Whereas from C to D, okay, let's say I'm traveling until 7 meters. If we were to compare the two situations here, alright, both have the same amount of time. Okay, 10 seconds, 10 seconds. But in situation 1, I'm traveling at a further distance. I can travel further in 10 seconds. However, in situation 2, within 10 seconds, I'm only traveling until 7 meter. And why does this happen? Very simple, very logic, right? It's because in situation 1, I'm moving faster. Very logical, right? Okay, both have same amount of time. But in situation 1, I can go further. Why? Because I'm moving faster lah. Okay, in situation 2, I'm moving slower. Okay, that is why in the same amount of time, from C to D, I only travel 7 meter. The total distance traveled here compared to situation 1. Okay, so let me now take this particular concept and apply it to this particular section here. Alright, Kepler's second law. Now, same exact thing. Okay, so I'm going to give you the time, alright? Okay, so let's say from A to B, the time travel taken is, let's say, don't want to use 10 lah. Let's say 24 days. Okay, both have the same amount of traveling time. Okay, but A to B, the distance that you travel is longer. Whereas from C to D, the distance that you travel is shorter. Okay, why? So the big question here is why? Alright, so based on this concept, same thing, right? The reason why here you travel further, here you travel shorter is because you are moving faster, right? So from A to B, the speed here is faster. Whereas C to D is slower. Okay, then the next question comes, but why? Another why. Why here faster, why here slower? Okay, it's because of your relationship between the distance of your planet and the sun. Remember in the first part of your lesson 3.1, we learned about what they call the effect of distance towards your gravitational force, right? Okay, if your distance between the two planets is smaller, your gravitational force will be higher lah. Correct? So in this case, from here, point A and point B lah, let's take these 2 points lah. The planet is nearer towards the sun. So if you are nearer towards the sun, of course the gravitational force will be higher, right? Meaning the sun's pull is stronger since you are nearer to the sun. So the sun will pull you even stronger. Therefore, you are going to move faster lah. Alright, when in case for C to D, okay, because you are further away from the sun, your gravitational force is weaker. So the pull is weaker. If the pull is weaker, you are going to move slower. Alright? Therefore, why? Okay, why? Because here from A to B, your gravitational force is higher or stronger. Whereas from C to D, your gravitational force is weaker. Okay, that is why here you move fast. From AB you move fast, and then from CD you are going to move slow. Okay, so basically Kepler's second law is that. Okay, that is the whole idea of the second law. Alright, so once you can understand this particular concept here, then you will know, okay, the relationship here, meaning that the what they call area of A, F and B will be the same as CFD. Okay, meaning this area will equal to this area. Alright, and the reason why it is the same is because of this particular reason right here. Alright, so this is what Kepler proposed. He said that based on his observation, alright, not observation, based on the theory, is that when you are nearer to the sun and you travel from A to B, right, the area here should be the same as the area when you travel from C to D. Although if based on visual, if you look like based on the diagram here, you will think that, oh, maybe this one will have a bigger area compared to this one. But in truth, it actually should be the same. Okay, so the area EFB will equal to CFD. Right, meaning if this one is, let's say, 100 kilometers square, this one will also be the same. Okay, because why? Because the amount of time is the same amount of time. All right, here your distance is longer, here is shorter, so the amount of area that you cover should be the same. Okay, so that is what Kepler's law is trying to say. All right, so I hope you can understand now, okay, what is going on around here. Okay, so basically this is just based on the concept of where the planet is. If you are nearer to the sun, you have stronger gravitational force from the sun will pull you, alright, then you are going to move faster. So if you move faster, you are going to travel further. Okay, alright, finally your third law. Okay, law of periods. Oh, right, I'm not even going to bother to read out this thing. Okay, so basically his third law, what is he trying to say is that if you are further away from the sun, you are going to orbit slower. That's it. Alright, basically the third law is based on this relationship here. Okay, if the distance between the two object or the two planet is what they call further, alright, your orbital period will also be longer. Okay, so very simple sun. Okay, I'm going to use standard tree drawing. Alright, let's say if I am here, okay, since I am nearer to the sun, it's the time taken for me to orbit will be faster, right? One complete. But compared to if I'm here, since my path is longer, right? Then of course the time taken for me to complete one orbit will be longer. So that is the meaning of the third law actually. Alright? Basically it's just trying to tell you, okay, the further you are, the slower you will orbit. Okay? Orbit slower meaning longer time lah, correct lah, because orbital period lah. Okay, so orbit slower meaning longer orbital period. Right, so basically that is the three laws of Kepler's. Okay, so it's actually not really that difficult. Alright, now let's look at how we get this formula right here. T squared, alright, derive Kepler's third law. So I'm just going to show you how we derive this. Okay, basically you are still going to use the two things. Alright, so you know this one is Gm m over r squared centripetal force. Alright, so basically we are going to take like mv, since we are going to equate the two relationships lah. Okay, so we are going to remove your m here. Alright, and then we are going to bring the r over here. Okay, so we are left with v squared here. Alright, so it will be g m over r. Okay, and then you know that v, your speed, is 2 pi r over t, right? So here over t squared equals to gmr. Alright, so you're going to get 4 pi squared r squared over t squared. Okay, equals to gm over r. Alright, so Right now, we are trying to use the Kepler's third law to calculate the orbital period. Okay, so in other words, period or orbital period is at this side, and this thing, the whole thing here, I'm going to shift to the other side. All right, now when I shift to the other side, it's going to become like this. Okay, because this whole thing divided by this one. Well, to those who are not really sure what is happening right here, all right, divide Em over R, right? So this one will become multiply, right? So R over Gm. So this whole thing multiply up. That's why you get this one. 4 pi square R cubed equals over Gm. Okay, so and then if I want to calculate my orbital period T, I need to square root the whole thing. Alright, but that is it. Okay, if you notice there's a similarity here with the one that we learned previously, the mass of planet. If you still remember, the formula to calculate the mass of planet is m and then 4 pi square r cubed over gt squared. So if you notice, right, basically we are just changing the position of the two variables here. Okay, the t squared goes here, the m comes here. Alright, so why do we need to do this? Well, basically, if I want to calculate the orbital period, after I rearrange the equation, it will become like this also. Okay, alright, so since this part here, okay, 4 pi squared over gm. Okay, now we know that these values here will always be the same. Okay, meaning here is a constant, it will always be the same. Therefore, we can simplify the equation so that it becomes like this. Alright, okay, meaning that this is a constant. Okay, and that is how they were able to derive the relationship, whereby t squared is directly proportional to your distance. Okay, now which tool will you be using for your calculation? Alright, so you have two formulas that you're going to use for your calculation. Okay, this is the first one. Alright, and this one will be the second one that you're going to use. Okay, so how do we use these two formulas here? Just like this. Alright, so a lot of people will ask me this. Actually, what is the purpose of the formula? Why do I derive the formula? What am I supposed to calculate? This is what students will always ask. Okay, I know this is a formula, but what should I use it for? Well, technically for Kepler's third law, right? What you are going to calculate will be based on the orbital period. Okay, and then this one is the radius. Alright, but how can we calculate these two things? So there are two ways for us to calculate. Okay, one is when they give us two planets. Alright, meaning they give me planet 1, the orbital period and their radius. Then planet 2, maybe they give me the orbital period and then ask me to calculate the radius. Alright, so basically, if you substitute this formula here, right, meaning this fraction here, okay, t1 squared over t2 squared divided by equals to r1 cubed divided by r cubed 2. Okay, basically the orbital period and the radius of the first planet divided by the second planet. Okay, this is if they give me the information for two planets. Then I use this formula to calculate. Alright, if in the question they mention about mass, then immediately you use this formula to calculate. Alright, meaning they give you what they call the orbital period, or they give you the radius, and they give you the mass of the planet. Then they want you to calculate the orbital period, then you use this one. This formula, if you see here, right, there is no mass here. Okay, meaning in this first equation here, the mass of the planet is not required in order for me to calculate T and R. Okay, because I'm using the what they call third law to derive the equation, this one. Okay, the fraction here. So easier said, if question do not mention anything about mass, they want you to calculate the orbital period or the radius, you use this formula. Alright, and then by right, they should give you the three, what they call three variables here, any of the three variables here. Okay, if there is involved with mass, then straight away you use this formula to calculate your period. But don't forget that you need to square root later on. Okay, you need to square root the whole thing. Right? So let me just show you an example right here. Okay, so Professor Nemo, that's me. Alright, the satellite is at a height of 400 kilometers. Okay, now remember, when involving a distance between two objects, okay, r can equal to this one, radius of Earth plus height, or radius of the planet plus the height. So since they already give me the keyword here, height, meaning I need to change this one. Okay, from the surface of Earth. Okay, so satellite. Okay, so let's say, so what do they want me to calculate? Orbital period of satellite. Alright, so let's say if I put T1 as my satellite lah. So orbital period of satellite, don't know. Okay, R1. Okay, the distance here, meaning I need to add up the radius of the Earth and also the height. Alright, so radius of Earth, oops, I think I forgot to give it here, never mind. Okay, plus, okay, 400 kilometers, so I need to change. You always need to convert to meter. Okay, so this one, you need to add up. So let me just quickly calculate this for you. 6 plus 400. Alright, so this one will be 6.77 times 10 to the power of 6. Okay, so this one is the first part. Alright, the radius. Okay, and then what else do they give me? Let me look here. Calculate the orbital of satellite. Okay, oh, they give me this one, right? Radius of the moon and also orbital period of moon. So I know T2, okay, of moon is this one in hours, right? Hours. Okay, then R2. The radius is 3.83. Okay, so I need to calculate for T1. Alright, so basically what we're going to do is we are just going to substitute the formula into this equation here. Alright, so T1 squared, don't know, over T2 squared, meaning 655.2 squared. Okay, and then 6.77 times 10 to the power of 6 square, this is cube, sorry, because this is r cube, divided by 3.83 cube. Okay, alright. Well, we are just going to calculate this as usual. You will get an answer here. But remember, this is t squared. So you need to square root your answer. Okay, so later on you're going to get your answer here in hours because we are using hours here. Alright, in this case, when you use the formula here, it's not necessary for you to change into seconds. Okay, just make sure that if the two time is given here, okay, so let's say for example, this is another type of question. If let's say they give me T1 is in what they call in seconds, for example, and then the T2, okay, they give me is in hours, let's say. Alright, and then they give me R1, just take this value here, easier. And then they want me to calculate for R2, right? Okay, now in this case, if both times or both orbital periods are given, but here the units are different, right? You need to change so that both are the same. Okay, so you need to remember this. For this particular formula here, this fraction, okay, when both periods are given, you need to make sure that their units are the same. So you need to convert. So it doesn't matter you convert which one. It's either you convert this one into hours or you convert this one into seconds. But both must be the same. Then only you can substitute into the formula. Alright. In this case, here they give me hours, right? So I just use hours and calculate. So that's why my answer here will also be in hours. Okay. Alright. So that is for Kepler's law. Done. Okay, so the next part will be about the satellite. Okay, man-made satellite. Alright, I'll see you in 3.3.